So what if I told you that less than 150 years ago, our entire understanding of reality was just wrong? Today, we are going to take a journey into the incredible story of how a series of revolutionary ideas completely shattered classical physics and built piece by piece this bizarre and beautiful new way of seeing the universe. We're talking about quantum mechanics.
Okay, so let's set the scene. It's the late 1800s, and physicists are feeling, pretty good about themselves. They've got Newton's laws, Maxwell's equations. It felt like they had it all figured out, from planets orbiting the sun to how an engine works. But there were these little cracks starting to show. When they looked at the super tiny, atomic scale, experiments were giving them results that made absolutely no sense. The old rulebook just wasn't working anymore.
So to see how they built a new one, we're going to follow this story like a relay race of discovery. We'll see how those first cracks appeared, how one radical idea got passed to the next thinker, from Planck to Einstein to Bohr, and how it all led to the totally strange world of quantum mechanics and, believe it or not, the technology in your pocket today.
So what was this big crisis? Well, it all started with something as simple as heat. I want you to picture a piece of metal glowing red hot. Now, according to the physics of the time, as it got hotter and hotter, it should have been blasting out an infinite amount of high-energy light. They called it the ultraviolet catastrophe because it was such a dramatic failure of the theory. It was a huge warning sign that something was deeply, fundamentally wrong with the old rules.
And just look at the incredible sprint that was about to happen. In less than 30 years, our whole picture of reality was completely redrawn. This right here, this is the relay team we're about to follow. It was just this rapid-fire succession of breakthroughs, with the baton being passed every few years. So let's meet the first runner at the starting block.
And that first runner is Max Planck. Now, Planck wasn't some wild revolutionary. He was just a really meticulous physicist trying to solve that one single annoying radiation problem. But in fixing that one little crack, he accidentally discovered an idea so radical, even he wasn't sure he believed it.
Planck's idea was this: what if energy isn't some smooth, continuous flow? Like water from a tap. What if it actually comes in these tiny, individual packets, which he called quanta? You couldn't have half a packet or a third of a packet. It was all or nothing. This was the birth of the quantum idea, the very first building block of this new physics.
And you know what? The idea worked. It worked perfectly. It completely solved the ultraviolet catastrophe, but Planck himself was really uncomfortable with it. To him, the universe was supposed to be smooth, continuous, not lumpy and weird. He actually thought his own idea was just a mathematical trick, a temporary tool to make the equations work, not a real description of how the world was. He had basically opened a door to a whole new reality, but was afraid to walk through it himself.
Now, Planck may have been hesitant, but the next runner in our relay race, he took that baton and absolutely sprinted. We're talking about Albert Einstein. In his miracle year of 1905, he realized that Planck's trick was no trick at all. It was a fundamental clue about light itself, a clue that Niels Bohr would soon use to figure out the atom.
Einstein's proposal was incredibly bold. He said Planck's quanta weren't just about how energy moves around. He said that light itself is made of these packets, and he gave them a name we all know today: photons. This meant that light, which for centuries everyone knew was a wave, was somehow also a particle. And this was the idea that really kicked the revolution into high gear.
With this one idea, Einstein was able to perfectly explain a totally different mystery: why shining light on a piece of metal can literally knock electrons off of it. The photons were acting like tiny billiard balls, and it all made sense. But the scientific community was not impressed. The idea that a wave could also be a particle was just way too weird, and Einstein faced years of resistance. He'd taken Planck's little trick and insisted it was real.
And here's the funny thing. Even though Einstein was one of the key architects of quantum theory, he eventually grew to be one of its biggest critics. He could just never accept the pure randomness and probability at its core, famously saying that God does not play dice with the universe.
Okay, next up was Niels Bohr, and he took these new quantum rules and applied them directly to the atom. He suggested that electrons could only exist in specific, quantized orbits, kind of like planets that were stuck on very specific tracks and couldn't be anywhere in between. This was brilliant. It explained why atoms don't just collapse in themselves and why they glow with very specific colors. But his model wasn't the final answer. It worked great for hydrogen, but it failed for basically every other element. It told us what was happening, but it didn't tell us why. The next pass of the baton came from a young French nobleman, Louis de Broglie, and he asked this simple,
elegant, and just absolutely audacious question. If waves, like light, can act like particles, well, couldn't particles, like electrons, also act like waves?
And this right here is wave-particle duality. It's the strange and wonderful heart of all of quantum mechanics. De Broglie's big idea was that everything has a wave, an electron, a baseball, even you and me. Now for big stuff like a baseball, that wave is so unbelievably tiny that you could never notice it. But for something as small as an electron, its waviness is a huge part of its identity.
De Broglie's idea was just pure genius. It finally gave the why for Bohr's model. The reason an electron's orbit was stable was that its wave fit perfectly around the nucleus, like a snake biting its own tail. But here's the catch. At first, this was just a wild hypothesis. There was absolutely zero experimental proof. It was just a brilliant guess that, as it turned out, was completely right, and it laid the groundwork for the final leg of our race.
All right, here we are at the final leg of the race. All the pieces are on the board. You've got quanta, you've got photons, you've got matter waves, and now, two physicists, working completely independently of each other, were about to build the full machinery of quantum mechanics. They took totally different paths, but they arrived at the exact same, very strange destination.
On one side, you had Erwin Schrödinger. He developed a famous wave equation that described exactly how de Broglie's matter waves behave. It gave us a much more intuitive picture of the atom. On the other side was Werner Heisenberg, who created a far more abstract, purely mathematical system using something called matrices. They looked completely different, but it didn't take long for physicists to prove that they were mathematically identical. They were just two different languages describing the exact same reality.
And out of Heisenberg's work came one of the most famous and most profound ideas in all of physics, the uncertainty principle. And the key thing to understand is this. It's not about our tools being bad at measuring things. It is a fundamental law of nature. The more precisely you know where a particle is, the less precisely you can know where it's going, and vice versa. The universe, it turns out, has a fundamental fuzziness built right into it.
So, the race was run. The theory was finally built. But what does any of this really mean for us today? This last part is all about connecting that incredible journey from the 1920s directly to the world we live in. Why does this all matter? Well, the answer is pretty much everything.
You see, this revolution didn't just stay in textbooks, it literally built our modern world. Those weird quantum rules are exactly what allow engineers to control electrons flowing through a microchip in your computer. It's why lasers can be so incredibly precise. It's the foundation of modern chemistry, of material science. Really, every single time you use a smartphone, you are holding a piece of applied quantum physics right there in your hand.
From Planck's reluctant little trick all the way to the technologies that define our age, the discovery of quantum mechanics was an absolute testament to human curiosity. It showed us that reality is so much stranger and, frankly, more wonderful than we ever could have imagined. And it leaves us with this tantalizing question to think about. A century after these incredible discoveries, where will the next quantum leap take us?